Should I start?
Hi, sir. You can go live now. We're all clear.
Yeah, so should I start?
Yeah, we can start.
Okay. All right. Good afternoon, everybody. So I'm going to give you a very short overview of the work we are doing to detect malicious accounts in permissionless blockchain using temporal graph properties. So first, let me tell you why we are interested in this. So we have been seeing that there has been a lot of fraudulent activities in blockchain, especially in the permissionless blockchain such as Bitcoin, Ethereum, etc., where people are using malicious smart contracts. For example, in case of Ethereum, they are using Ponzi schemes. They're doing gambling. They're doing various phishing activities on the blockchain, and also they're floating malicious smart contracts and then engage people to use them, and thereby creating various kinds of activities. And also money laundering is another activity that we are seeing. Now, in the past, we have done some study on Bitcoin and Ethereum, and we found that there is an immense amount of inequality in those ecosystems. So 90% of the ethers, for example, belong to only about 1% of the accounts. So we have seen also the smart contracts. There are a large number of smart contracts with cyber vulnerabilities, and they have been exploited. As we know that in one case, the DAO attack, when a lot of ethers were stolen. We have seen various activities by malicious exchanges. So we thought that it is important that there should be a way to detect when some accounts start behaving maliciously. And the maliciousness in this case, we actually look at accounts that are doing like they're designed to do Ponzi scheme, money laundering, various kind of phishing, uh, gambling, these kind of activities. So the question is, how do you detect these things? So the best way to detect these things is, of course, by vigilante people who actually observe certain accounts and their behavior. Now, in case of Bitcoin, this is a little bit more complex. We have done separate work on that, because in Bitcoin, every time you do a transaction, you create a new identity for the culture change address, and therefore tracking a person is more difficult. In case of Ethereum, you have a notion of account and account balance, and transactions often happen from the same account again and again, and therefore it is slightly easier. So we'll talk about the Ethereum case today. So the way we do this is by first, one good thing about this public permissionless blockchain is that you have all the data, all the transaction data you can download from the Genesis block all the way to to today if you want. But since we did this work last year, so therefore our data spans till sometime in 2019. And then to do validation, we have used data until about July 2020. So past activities of accounts is a good indicator, especially if you know what kind of account it is. So Etherscan actually provides you some of this crowdsource catching of this kinds of accounts which are involved in this kind of activities. So you can use them to actually understand the behavior of phishing accounts, behavior of Ponzi scheme accounts, behavior of money laundering accounts, this kind of stuff. But also, in some cases, you don't have those markers and or tags. Therefore, you may have to go without having those what we call labeled data. And in those cases, we have to use unsupervised learning. So you can do supervised learning if you have some labeled data. If you have if you don't have enough labeled data, then you have to do unsupervised learning. So, so what we found, first thing we noticed is that I already told you that we found there is huge amount of inequality in this ecosystem, and then we found that all the accounts, they have very different behaviors, and depending on whether they're malicious or they're non-malicious, their behavior changes. So the question is, can we train machine learning model to detect such activities and generate alerts? Now, this is not something that we thought about for the first time. There has been quite a bit of work on using machine learning to detect such activities. But what was missing in those activities is that they considered blockchain as a frozen snapshot, blockchain data as a frozen snapshot in time. So the time they actually collect the data, until then, every block has made many transactions. Every account has done many transactions on many blocks, and they actually construct graphs like which account gives money to which account. So there will be an an edge, a directed edge. If the accounts are modeled as nodes in a graph, then they will create edges. If account B gives money to account A, then there will be an edge from B to A and things like that. Now, what they have done in the past is that they have considered this as an aggregate model. That is, when they collect all the data, they will create graphs that will have all the edges. So maybe the in block number 1, B gave money to A, and block number 17,000 again B gave money to A. So you will have two edges, but it won't tell you which block and how far apart they were. So these kind of temporal nuances of these activities were not captured. So that's the main thing that we have done here, is that we said that, well, don't consider it as an aggregate graph, consider it as a temporal graph. Second thing that we have found is that when you consider these graphs, there is a lot of bursty behaviors. That is, most accounts do very little activities, but there is a significant number of accounts which do a lot of activities. So for example, in degree and out degree of the accounts. In degree means how many other accounts have given money to this account, and out degree means how many different accounts to which this account has sent money. And we found that in most cases, the low numbers are very high probability, but there is a small but not insignificant amount of activities by some accounts which do a lot of transactions. Same thing we saw this in case of out degree, and similarly we saw that inter-event time, that is time between two subsequent events by the same account. There also accounts tend to do things in a short period of time, but there are accounts which actually remain dormant after one transaction for a long time, and then they actually again do a transaction, this kind of activity. So again, the graph kind of follows what we call a power law. So same, another thing that we found is that the malicious accounts that are involved in malicious activities, they tend to interact with newer accounts as time goes. So it's not normal accounts. They actually tend to transact with certain number of accounts that they always transact with. Whereas malicious accounts tend to change who they transact with, and that's what we call neighborhood. And so the what we say is that malicious accounts show a very low stability of neighborhood. That is, they always try to interact with, they always tend to interact with more, newer and newer accounts, and that is something also we noticed. So having noticed all these things, we said, okay, so if we are going to learn the behaviors, we have to consider temporal variation in the behavior, and we also have to think of their burstiness, whether the malicious accounts are more bursty or regular accounts are more bursty, whether their inter-event times are more closely spaced for malicious accounts or for regular accounts. And then we also look at the neighborhood stability, this kind of stuff. And so by collecting the data set, we pre-process them to do feature construction, and we take two paths. One is a is a supervised learning path, and another is an unsupervised learning path, right? So that's basically what this picture is saying. Since this is a short talk, we'll not go into too much details, but you get the idea. Now, where did we collect the data from? So we went to Ethereum mainnet, and then, of course, the number of malicious accounts that have been marked malicious. So this is, I'm talking in the context of supervised learning. So we found about 3,000 malicious accounts, whereas there are a huge number of non-malicious accounts. So we have to do an undersampling. So whereas the regular ratio of malicious versus non-malicious account was 1:23,500, we undersampled so that it is 1:233, because otherwise with an unbalanced data set, it's difficult to actually get good results, to get generalizable machine learning. So we take so about 700,000 accounts, of which majority 697 was benign and 3,000 were malicious. And there were two types of accounts in Ethereum. That is the accounts owned by people, and then there are accounts that are basically smart contracts. So you have to also see whether which of the smart contracts are malicious, and in which cases the individual accounts, externally owned accounts, EOS, are malicious. And as I said, that the malicious accounts are phishing, scam, hacks, etc. So we took from Genesis block till the December of 2019 data, and then we did the necessary pre-processing, data cleaning, etc. And then we did feature construction. So some of the features that have been used by attacks are burst based, and some of them are like, for example, degree. We already showed you that the degree has a bursty behavior, temporal distance has a bursty behavior, transaction amount has bursty behavior, gas price also has bursty behavior. And then we also look at in-out degree, balance in and balance out, maximum in payments, maximum out payments, gas price, and attractiveness is basically a measure of the neighborhood stability, inter-event time. Now, again, since we are not looking at the aggregate data, we are looking at the data as things go, as new blocks are added. So we are actually constructing graphs. Like every account has now in degrees that varies from block to block, right? So out degrees vary block to block. So we create these temporal graphs. And then We also take some non-time series based features like when an account transacted first, when an account transacted last, how long the account was active, last active since, like when was how much time has elapsed since last active, zero transactions, how many zero transactions they make, unique neighbors or unique people who interacted, unique accounts who interacted with this, and clustering coefficient, etc. So as I said that the burstiness of degrees, so it seems like from our data we found that incoming and outgoing transactions tend to be very high in number in a certain block or in two consecutive blocks for certain types of malicious activities. So here is a kind of a picture that shows that at this point there is a huge number of outgoing and incoming transactions for this account. Other times they're normally transacting. But if there are such bursts, then we see that we consider that as possibility of some malicious activity, like all-in-vain theft, for example, displayed such features. So similarly, how closely spaced are their activities? Like are they like doing activities one after the other, or they are taking their time, like doing an activity now and then staying dormant and staying activity. So we saw that the gambling accounts seem to have temporal bursts. So similarly, transaction accounts, like so there is burst in transaction amounts, and we saw Silk Road accounts had such transaction patterns. So similarly, a gas price also has similar behavior. Now, attractiveness is basically a measure of what I earlier said, the neighborhood stability. Like, do you interact with the same set of people, or do you interact with all kinds of people all the time? That's basically is measured in terms of attractiveness, that we defined as this measure. We'll not go into the measure here, but you can imagine that a normal account will have more or less good stability, whereas the malicious accounts seem to be always hopping from interacting with certain certain accounts, and then they're moving on to interact with some other accounts, and not staying stable in terms of their neighborhood. So this is an example of such thing. Like if you look at here, the A, so A is being interacted with a lot, and they're more or less always interacting with either with B or C or D, etc. Right? So therefore, it seems like the A has an attractiveness, high attractiveness, right? So therefore, A's neighbors is not stable, right? So it changes its partners, right? Whereas things which don't change their partners that often are least attractive accounts, and turns out that malicious accounts are more attractive. Now, I also said that certain aspects of these accounts we actually plot as a temporal graph. That is, every timestamp we actually see how many times they actually interact, or how much money they interact, etc. So with this time series graphs, we actually, but we cannot use the time series graph as it is in the machine learning. So what we do is that we actually use TS-Fresh to extract features, and TS-Fresh extracted huge number of features for each time series. So these features characterizes the time series. Then we use top 3 features with the high Gini coefficient. So that's a way of reducing features. The most significant features are kept, and then with all this pre-processing, we found a total of 59 features. Some of these features were highly correlated. So we actually removed them by doing pairwise correlations, and then we get 36 features. And then if we use some machine learning feature reduction mechanism like PCA, the principal component analysis, then we can bring it down to 28 principal components. So let's see what the results are. We look at the results in terms of accuracy, balanced accuracy. That is how accurate it is predicting malicious accounts and how accurate it is predicting benign accounts. So, and their average is balanced accuracy. So we see that the balanced accuracy in this case with reduced features is about 87%. With all the 36 features, we can get it up to about 88%. And then with all 59 features, we get it for 88.7%. Now, one thing I should also note is that the recall values, the recall basically tells you that how much how good we are with in terms of false negatives. So false negative is means that you will be calling recall basically tells you how bad we are with respect or how good we are with respect to false positive. So which means that how many malicious accounts you are actually marking as benign. And this number here seems to be pretty respectable, that is 75+%. So which we felt that it gives pretty good accuracy in terms of as far as learning goes. We also use unsupervised learning for accounts, and the way we do that is we use clustering. And so we actually take these features, and then these features construct a vector space. With the feature vectors, we get vector space, and then we actually consider Euclidean distance in that vector space, and then to see who are how many clusters we get. And if our if our feature space is good, then all the malicious guys should cluster together, and all the benign people should cluster in different separately, right? So that next time onwards, when I get a new account, I look at its history, extract the features, and then I try to see how far it is from the cluster of malicious and how far it is from cluster of benign. If it is near or inside the cluster of malicious, then we know it is malicious. If it is in the cluster of benigns, we know that it is benign. So, and to know how good my clustering is, we actually compute the cosine similarity and the silhouette score. So this is the silhouette score figure. So you see that malicious ones actually cluster together pretty in large numbers, not 100%. So using this, we have found extra 554 accounts of externally owned accounts, and 293 accounts in mixture of externally owned and all accounts. Now, what we found is that most of these accounts which have been predicted by our algorithm as malicious, they have been dormant for a while. They haven't transacted for a while, or having only incoming transactions with a very high attractiveness, that is less stable neighborhood. So most cases, this must be either a Ponzi scheme account or it might be a phishing account. So then now how do we use this in real time, right? So the question is that can I plug in this model to Ethereum and start predicting or cautioning users when they try to interact with an account, by telling them that what is the probability that the account they're going to interact with is might be malicious. So for that, the question is how far in the history of the account should I look in order to make a prediction. So that's what this experiment is all about, that we wanted to look at different time spans. So daily, like what happens in a day, is that enough to predict? Or what happens in 7 days with that account, is that enough to predict? Or should I have to look at 1 month of data? Should I have to look at a 1 quarter of data? Or should I look at 6 months of data? Or should I look at yearly data, whole year's data, in order to say whether somebody is malicious, right? Because if I make a decision based on only last 7 days of data, maybe that account remain dormant, right? So I may have to look at its behavior over a month or maybe over a year. That determination has to be made. So while doing that, what we have done is that we said that we found that lot of these accounts, they change. If I look at a certain time scale, and then if I look, so I have about 5 years of data. So if I look at this guy engaging in malicious activities in the first year, second year maybe it is quite dormant or doing nothing, or maybe doing very little or spending that money like a normal account. So this way, malicious, something that is determined malicious over a year may look benign if you look at its behavior in the next year. And then if you look at the next year, it may again look malicious. So this kind of behavior we are seeing, and therefore, at least for about 10,000 accounts. So we assign a probability to an account to be malicious by looking at how many times it changes its level for being marked malicious, being considered malicious to benign and benign to malicious. So this we feel is that, and we found that 814 such accounts has a probability of being malicious was very close to 1. So that means that there are, and these accounts we were not marked yet by Etherscan or anybody. So what that means is that if our calculations are right, then these accounts are pretty dangerous accounts, and people should be discouraged from interacting with these accounts. But the problem with that is that we cannot really publish the addresses of these accounts, because they might feel offended that they have been marked malicious just because their behavior kind of looked malicious, right? So that is something that we have to still figure out how to better validate this, and that's something we are doing in terms of ongoing work. Now, while we were finishing this work in May 2022, we found that in the meantime, Etherscan has tagged another 1,252 accounts as malicious. So when we applied our classifier, we found that we could not get any of them detected as malicious. However, if we take 10% of them, that is 125 of them, into our training set and retrain our model, then we are able to successfully detect the other 90%. That is, all the other ones we are able to detect. Now, what that means is that the behavior of maliciousness is also very much changing. So what we learned from the behavior change, the behavior as malicious or as non-malicious changed over time, because these guys are also behaving differently, or they came up with a new way of being malicious than just Ponzi scheme or phishing, etc., because they are being marked by Etherscan. So that itself, it throws a challenge, because now our model has to be retrained all the time, as more and more malicious accounts get flagged. So that basically is the lesson from this additional data that we got until May 2020. So that's basically what I have in terms of this. So we presented a way to detect malicious accounts considering the temporal nature of blockchain. We used graph-based temporal features, and we performed behavioral analysis over various timescales. And through that, we were able to assign probability of being potentially malicious. And we currently are working on using reinforcement learning so that model can continuously learn and modify itself, learning from the newly tagged malicious accounts. That's the last thing that I showed, that the malicious behaviors pattern also changes over time. So therefore, we need to relearn some of these behaviors. So I think that is what I wanted to say. So I will unshare so that if you have any questions, I'm going to address them. I cannot hear you.
All right. Oh, so I was on mute. Yeah. So, is anyone having any question? You can fire up to Sandeep sir. He will be with us answering those questions. So, anyone up? We'll wait for 5 more minutes. And I want to thank to you, sir, for sharing your phenomenal knowledge with us. It's our pleasure to have you with us in this Unchained Blockchain Security Conference. People will love you to see your sessions recorded even after the conference.
Okay, sure. Now,
Right? Yeah. We'll wait 1 or 2 minutes to if anyone is having any question, then we'll wrap around. I think no one is having any question. I think they
okay,
all understood everything. So thank you once again, sir, for joining our conference as a speaker. It's a
sure.
privilege to
My
have you with
pleasure.
us. Yep.
All right. Good luck with the rest of the conference.
Yeah. Thank you so much. Thank you once again, and see you, sir. Bye bye.
Bye.
Hello. Hi, Tejaswa. Can you hear me?
Hi, sir. Can you hear me?
Yes, I can hear you.
Uh, yeah, it is. Hi, sir. How are you?
I'm doing good.
Yes, sir. So we are very
Thank
excited
you.
to have you with
Friday.
us. Yes, so
It's a
finally
Friday.
I'm here to host you. And for the first time, we are meeting each other as a host and a speaker. It's a wonderful feeling right now.
My pleasure, Tejaswa.
Yes, just tell me when you want to go live. I will share your screen. Okay. Now your screen share is live,
Okay.
and you can go live, sir. We are all ready
Can you
for
give me a
your
moment?
session.
I will close other screens.
Uh, you can, yeah, you can share your tab as well if you want to. Yep.
One
It- it-
second. Just let me publish this slide,
yeah, sure.
and so it will be visible to everyone. So published. So window. I hope is it visible?
Yeah, so it's invisible.
Okay, so let me come back here. You are able to see here, right?
Right.
Okay, let me check. Are you able to see the pop-ups?
Yes, I can.
Right. Okay, so I think I am mm, got it. So let me come back to my slide. Okay, here we go. I'm ready. Tejaswa, hello.
Yes, sir. I'm going off here, and the stage is all yours.
Great. Thank you so much. Hello, everyone. I hope you can see me and hear me. Let me switch over to my presentation. This is about ZK rollups, an enigmatic engineering technique for Ethereum ecosystem, powered by a very exciting and elusive technology called zero knowledge proofs and a beautiful technique known as rollups. Let's get into the concept of ZK rollups. Why do we need ZK rollups? As we see in the coming in the last 2 years, there has been a lot of external smart contract calls in Ethereum thanks to decentralized finance. We know there are a lot of new lending protocols, a lot of banking protocols which depend on a lot of external smart contract calls like oracles. We call them fondly oracles. These oracles get the price feeds, real time data, and real time interest rates, real time data from decentralized exchanges, centralized exchanges, uh, the dollar price feeds. So these external smart contract calls are rising and rising again. And we know there are some protocols like Chainlink and Teller, a lot of smart contracts right? So that's the that's the specter of external smart contract calls, and due to that, we have seen the median gas price on Ethereum ecosystem has skyrocketed. And then came a famous tweet from Vitalik Buterin, the inventor or the founder of Ethereum protocol. He came up with a roadmap where he talks about the promise of roll-ups on Ethereum. And all of us know there has been a lot of technologies, layer 1, layer 2, even in the 2018-19 in Ethereum. But we're hearing the term roll-ups quite often in the last few months and I would say few months. So in this diagram, Vitalik is showing how we need to transition from Ethereum layer 1 to eventually Ethereum 1 rollups to finally Ethereum 2 plus rollups, which could promise us a great uh, exponential rise in the number of transactions per second. And it could initially be doing for simple payments, and it could even promise us to advanced use cases like decentralized exchanges, lending protocols, games, etc. So what is a rollup? It's a solution that bundle up or roll up sidechain to a single transaction and generate a cryptographic proof. Now we are hearing new terms like sidechain and a somewhat different term like proof. Proof is something we studied in our school mathematics classes, but is that the proof here? What is a sidechain? Let's first understand sidechain. But before going to sidechain, let me explain the concept of rollup in an Ethereum smart contract perspective. A rollup is defined as a off-chain aggregation of transaction inside a Ethereum smart contract that reduces fee and congestion by increasing the throughput of the blockchain from the current 15 transactions per second to more than 1,000 transactions per second. That means in a smart contract, users can transact with security guarantee for their transactions that it will not be misused. And they'll be able to settle to the main chain at some point in the future. So it means it is publishing just enough data on chain. So with this just enough data on chain, observer can reconstruct the state and validate the transactions and detect any invalidity or fraud. This sounds a little bit complex, but we have to understand this in perspective, right? Ethereum is a state machine. Ethereum is not a single transaction machine like the Bitcoin, as we mentioned in the Bitcoin is a very simple valid transaction model with a UTXO model. But in Ethereum, it is engineered as a state machine with multiple Merkle trees for different states. Like we call it tri. It's not a simple Merkle tree. We call it a Merkle Patricia tri, right? And because of that, you need to verify the state on chain. So that is the last part of this statement. Any user of the chain should be able to reconstruct the state and verify it. That's the last part of the statement. So what is the benefit of a rollup? Rollup will help you to do so many things in a single contract. You can aggregate lot of transactions, off-chain transactions into a smart contract, and it reduces fee and the congestion, because if you do so many things, so many smart contracts, it will be congested. So you're reducing the need for more number of transactions, and as a result of it, you are able to do transactions per second, adding off-chain plus on-chain or layer 2 plus layer 1. The net the number of transactions are more. One smart contract could support multiple or hundreds of off-chain transactions. So what is the history of rollup? The concept of rollup dates back to early 2014 itself, described as shadow chain by Vitalik co-founder, the Ethereum co-founder Vitalik Buterin. So if you there is a perception, or there is a commentary, that plasma and state channels were not as successful as it was required to be for the layer 1. That's why Vitalik has highlighted the need for rollups. There is no doubt plasma and state channels can scale millions of transactions per second, as we are seeing in plasma implementations, the plasma adaptations like Matic, and other state channel implementations like that we see in Connects network and etc. Right? They can scale millions of transactions, but how much of that can be done in layer 1 plus layer 2 combination? Perhaps that is the reason rollup has been, Vitalik has actively evangelizing, actively supporting rollups in the recent years. So let me first show the concept of shadow chain, in concept which was introduced in 2014. So there is a main chain, and then there is a shadow chain where there are unfinalized blocks and finalized blocks. Shadow chain blocks are finalized after some time. So shadow chains take more time. You are deferring or delaying the confirmations in the shadow chain. So shadow chain participants do not verify blocks by default. After 2 weeks, there is no revert, and chain runs parallel to the main. But it does not shadow all the data. The main idea is to separate the data which is cheap to store and to execute the smart contract which uses more gas. So there are two things. You take the cheaper data and the complex smart contracts into the shadow chain. That was the idea for shadow chain. So shadow chain concept take all the computations off chain, while state transitions are committed to the main chain, because as we mentioned, state, the confirmations is very, very strategic and important to a replicated state machine like Ethereum, right? It has a state tree. State tree is very strategically important for the entire Ethereum main chain. So right now, even there is a proposal calling stateless Ethereum, how to design stateless clients to Ethereum to make them lightweight. Now, there is a proposal to make the Geth stateless eventually in the Ethereum 2 roadmap. We are not going deep into that, but coming back to Ethereum engineering, now when we talk about state transitions, they are applied automatically to the main chain if blocks are unchallenged after a particular period of time. Block is reverted if somebody can successfully challenge it before it is committed. This concept of reverting a block is very interesting, and now even it is powering some of the very promising concepts like even flash loans. Flash loans are even powered by concepts like the reverting of a block when absolutely it is necessary. So shadow chain to rollups. What is the logical connection between shadow chains and rollups? Rollups built on shadow chain idea by taking the execution of state off chain and only using blockchain for data availability. This is the interesting thing. State is taken off chain because we can do it through rollups. And we use blockchain only for data availability. So what happens is rollups post, block, or publishing something for each transaction through a particular operation code called data in the contract, which gives improvement in throughput and overcoming a major on data withholding attacks, which if somebody can withhold the data in a lot of other scenarios can come up when you look at the data availability related attacks. So rollups takes the idea of off-chain engineering to a next level, where rollups post block or state updates, only publishing some data, minimal data to the main chain. Transaction data. So this is a very simple diagram to show how the rollup chains work. There could be multiple rollup chains connected to the main chain. Now let us understand what is a sidechain and a little bit detail. Sidechain is a scalability technique used by various blockchain protocols. Plasma is the name given to the construction of scalability method that places layer 2 block on the top of Ethereum blockchain in the form of sidechains. Plasma has been one of the most popular sidechain technique in Ethereum. So Plasma gives the ability for hundreds of sidechain transactions to be processed offline with only one single hash of the sidechain block being added to the Ethereum main chain. So with Plasma, you can do hundreds of sidechain transactions, processing them off-chain with only single hash of the sidechain added to the main chain. This diagram depicts Plasma in a beautiful manner. So the Plasma permits chains with chains, allowing exponential increase in scalability. So there is the concept of child chain. Validity of child chain is submitted and stored on the parent chain. You don't do the entire child chain computation onto the parent chain. So the interaction with the root chain is absolutely necessary only in the scenario of a dispute, only for dispute resolution. So child chains are there, which are connected to the root chain. But even to the Plasma model, we understand there are challenges. One of the practical challenges, there should be a game theoretic model, like an exit game must be played for the user to withdraw from the sidechain. And it requires sidechain users to retain high amount of data so that it is sufficient for the validation. And there is also the mandatory challenge period for users to stay online and lose the reward. So these are game and engineering constraints in the Plasma model. What are the benefits of the rollups over the Plasma model? Before going there, I can for a moment if there are any questions. Or how do we take the questions? Are we taking questions offline? Okay, so let me proceed. No questions till now. So let's get back to the presentation. What are the benefits of rollups over Plasma model? Plasma, while creates one transactions per transfer, rollup can bundle hundreds of transfers. The smart contract will to deconstruct these batches, bundles of transactions, and verify all of them held in a single transaction. This is the beauty of rollups. Rollups, while they bundle up, the smart contract has the power to deconstruct and verify all the transaction held in a single transaction, all the transfers held in a single transaction. There are two broad approaches to rollups: optimistic rollup and ZK rollups, which we are studying in detail today. The key difference in optimistic rollup and ZK rollup is the way they differ in the way they ensure validity of the side block. Optimistic rollup, validity is ensured by a fraud proof and by a synchrony assumption, a time-related assumption. While for ZK rollups, validity is ensured by zero-knowledge proofs, a new term for us. See, in optimistic rollup, we verify fraud proof or there is any invalid block, and we also check the time synchrony, right? But for the zero knowledge proof based rollups, we verify. Let's see what's ZK rollup in a nutshell. Zero knowledge is used to send and publicly record the validity of the block on Ethereum blockchain. So the benefit of zero knowledge proof based ZK rollup is it reduces computing and storage resource for validating the block by reducing the amount of data held in a transaction. Now let's see what is zero knowledge proof. When you look at the history of zero knowledge proof, this was first introduced in 1985 by three famous cryptography researchers known as Shafi Goldwasser, Charles Rakoff, and Silvio Macaulay. And it first appeared in New York Times in 1987. That's the most interesting. They didn't write it in any interesting IEEE journal, or they didn't publish in academic journals or university publications. Instead, they published in New York Times. This is just like how in 1977, RSA Group published in New Scientist or Scientific American, I think. So, what is zero knowledge proof? They designed the notion of knowledge complexity, a metric for amount of knowledge that is needed for transferring from a prover to verifier to consider it to be valid. So, the zero knowledge proof is a very strange term. What it is, it's a notion of complexity of a knowledge or computational complexity of knowledge, a metric for amount of a transaction. Can you give me a moment? I'll just switch off my camera for a moment. Noise now. Okay, getting back to the presentation. Okay, so it is very important to understand this is a paradigm in the theory of computational complexity. This is perhaps first time we have used the construct of knowledge in the world of computational complexity or computer science, quantifying the amount of knowledge that is required to transfer information from an informal entity known as prover to a powerful agent known as verifier, to consider that to be computation. This, let me show the press, the archive. This is the New York Times where this article was published. It's written as new developed. the press release article. As you can see, if you refer to that article, you can see it's talking about blending pure logic with computer technology. Please understand, this is written in 1987. This text is from 1987. It talks about blending pure logic with computer technology. Researchers are developing an area of mathematics known as zero knowledge proof, where a conventional proof conveys information. A zero proof is meant to convey only the assurance that the information is in hand. So, zero knowledge proof is present new metadata about information that it is an assurance about knowledge. The assurance is a metadata which does it about the information. The goal of zero knowledge proof is to convince a second party called verifier of the knowledge that allow him or an eavesdropper to convince the party. So this is a transaction between prover and the assurance that this information is email information. With this information, no adversary can use this information, exploit this information. So nobody can use this information to understand more about the information. So it's like an assurance on the top of information. So you are hiding unnecessary details about information through a cryptographic assurance or knowledge proof. Zero knowledge proof life, like in the initial years, it was interactive proof. That is why in this newspaper article it talks about interactive exchange of information between prover and verifier. But nowadays we have very sophisticated non-interactive proof systems. Here it was interactive, so there is a need for a kind of exchange of information or actual prover and verifier. Even in 1987, it was considered as a significant break from traditional practice of proof forever. So, you know, in traditional cryptography, you were writing proof once and for all. For example, in your traditional systems, you write the password for all. You can't use the password, but that remains as a proof. Or so normally you use private key, or you can't change it through cycles. So this is a break from traditional practice. One of the most respected computer scientists of our time, Manuel Blum from UAE, who was the teacher or mentor to many of our time. Like he was the doctor advisor to many famous cryptographers like Silvio Macaulay, who authored zero knowledge proof. Manuel Blum said, "What if most exciting whole notion mathematical very prophetic in that statement. Zero knowledge proof opened up a new paradigm for privacy preserving proofs and then verifiable credentials and incomplete information games and so many other things." So Dr. Macaulay, the doctoral student of Manuel Blum, Shafi Goldwasser, Charles Rakoff, Oded Goldrich, and Wittgerson, they have applied zero knowledge proof first time for prove the problem known as graph coloring problem. They could prove that such a very computer difficult problem such as graph coloring problem itself could be verified. The proof could be verified without disclosing the complete proof. See, graph coloring problems are computer problems. Even for those formal problems, you could give zero knowledge proof. That was the potential of knowledge proof. Even though this is from the 1987, mathematicians speculated even that we could use zero knowledge proof signing contracts or communicating orders to stockbrokers. And now we are talking about applying zero knowledge proof for smart contracts in 2000. So what are the milestones in zero proof? In 1985, the first zero proof was written in this paper, Knowledge Complexity, Interactive Proof System. So you are measuring the complexity of using knowledge in interaction. That was the initial paper. And, perhaps those days, Alexandro Chiesa was just, and in 2012, Alex came with research ZK-SNARK. ZK-SNARK is something known as zero knowledge based non-interactive arguments of knowledge. That was revolutionary. And in 2016, Zcash protocol released, and they became cryptocurrency using ZK-SNARK, the concept proposed by Alexandro and his team, formed other researchers like Dr. Elin Sasson. So what is the significance of Zcash in the zero knowledge journey? Zcash is the first use case until then, provers and verifiers had to interact with each other in multiple rounds. Be convinced of the provers. When you go into the theory, there are three essential criteria like soundness, complete, and the soundness, completeness, and zero knowledge proof criteria. So there were multiple rounds of interaction required between the prover and verifier for in the traditional interactive proof setting, but that was no longer necessary in the ZK-SNARK model. Okay, now let us see in brief what is ZK-SNARK. Requires something trusted setup to start the system, but there is a challenge to it. Information used in the startup, the trusted setting, if it goes into the wrong hand, that information is known as the toxic waste. The toxic waste comes in when you try to create the private key and the randomness used by the witness in the computation done by the prover. So this toxic waste is in the hand of an adversary or the wrong hand. It could jeopardize and corrupt the entire system. So the trusted setup ceremony had its constraints and challenges, and hence they did a workaround by destroying the private key that was used, and the computers that were processing them were destroyed in the ceremony. Then came an alternative. In fact, two alternative came: bulletproof and ZK-SNARK. ZK-SNARK is worth mentioning here because it's being even used in ZK rollups now. Trusted setup phase is considered vulnerability, as we have seen, because the people need to trust that the information used in the setup was destroyed properly. To fix this shortcoming, ZK-SNARK was created. It's a kind of zero knowledge proof that does not require the trusted setup. It uses an interesting method, cryptographic hash setup. New kind of polynomials and hash functions going into the roll-ups, let us also Aztec that brings its Ethereum network by privacy for smart contracts. So essentially, Aztec was private Ethereum tokens and so in the given so using is there any connectivity issues? Hello, can you hear me? Let me check the Hello, can you hear me?
Hey, sir, I can hear you. It's all good.
Okay, thank you. Sorry for the inconvenience.
It's
Let
all
me
right, sir.
quickly,
Like,
let me quickly take you to the presentation. So now let's deep dive into Tejaswa. Can you please tell me you're still able to hear me? Hello, am I audible, Tejaswa? Okay, I hope to all of you. I'm continuing the session. Let's continue into the slides. We are deep dive into the roll-ups now. So initially proposed by Barry Whitehead in 2018, ZK rollups, they have the same security guarantee as the underlying layer 1 technology, like Ethereum. The potential to produce blocks under a minute and increase the throughput to as high as 2000 transactions per second. There are projects like Matter Labs, Identree, and Starkware on ZK rollups. So instead of waiting for 2 weeks for the blocks in the shadow chain to be finalized, ZK rollups replace fraud challenges with zero knowledge proofs, and hence it provides instant finality. Accounts and balances are represented by separate Merkle tree. This is important to understand. I hope all of you are familiar with the concept of Merkle tree, which is the basic data structure of a blockchain. Here in ZK rollup, we construct two different Merkle trees. One Merkle tree for accounts and another Merkle tree for balances. These Merkle tree roots they ensure no one can fake the data, because Merkle tree is a very powerful data structure to verify the end-to-end data accuracy. Like the entire tree, even if one single node changes, the entire Merkle tree changes, right? That's how the roots and the parents and the child nodes are connected. The roots of each Merkle tree, one for the account and another for the balance, are both stored in a smart contract in Ethereum. So the root of the account Merkle tree and the balance Merkle tree is stored on a Ethereum mainnet smart contract. That provides the succinct representation of the state of the sidechain. So all the other data is stored on off-chain. So here the state of the sidechain is stored on a smart contract with succinct proofs. We heard about succinct earlier in the snark. So the snark proof of the sidechain state is stored on a smart contract for two Merkle trees, account tree and the balance tree. So this is how it looks like. Merkle root and the account data. Likewise, balance data also will have another Merkle tree. How is the workflow of ZK rollups? ZK rollup consists of two types of users: the transactors and relayers. Transactors create the transfer and broadcast the transfer to the network. And the transfer of data consists of an indexed version of to and from addresses, a value to transact, and a network fee and a nonce. So the data structure of the transfer consists of a to and from addresses, a value, and a fee and a nonce. So the shortened 3-byte indexed version of the address, it reduces the processing resource needs. The value of the transaction, every transaction value is checked, whether it's a greater than or zero, or a greater than or less than 0. Whether, so that based on that you can deposit or withdraw. This is the, so you can do either, you can, so you can do deposit transaction or withdrawal transaction. It depends on how much balance you have. If you have negative balance, if you have zero balance, you can't do it. Only if you have positive balance, you will be able to do the withdrawal. So as we said, there are two Merkle trees, address Merkle tree and the balance Merkle tree. Okay, so there are two type of users, transactors and relays. Relays relay the information, transactors do the transactions. And what does relays do? Relays collect all this transfer information and they create the roll-up. So the transactors create transaction, relays relay this information to generate the snark proof. So the relays are the proof generators. They roll up the transactions into a snark proof. Snark proof is essentially, it is a hash, that it's a hash of a blockchain state or the delta state of blockchain. Delta means it is not committed yet. That is called state of being. The snark proof compare the snapshot of the blockchain before the transfer to the snapshot of the blockchain after the transfer. So this is like the version control systems, right? You check the previous and the current version. So you take a read-only snapshot of the blockchain before the transfer and you compare it with the snapshot of the blockchain after the transfer and report only the changes in a verifiable hash to the mainnet. This is very interesting. We used to do this kind of a model in earlier version control systems and the earlier systems where we used to do snapshot. Even in a lot of database systems, snapshots are a standard technology. It's worth noting that anyone can become a relayer. So as long as they have staked the required bond in smart contracts. So just like staking in an Ethereum 2 or in other related proof of stake protocols, anybody with a definite stake can become a relayer. And this is the game theoretic model. So it's very important that a relayer has a strategic role. That's why relayers have to stake the required bond in a smart contract so that they don't, we mentioned about data withholding attacks. They don't tamper with the data or they don't withhold data. So to look at this dynamics in a little bit more engineering detail, transactions are aggregated together into rollups, then they are signed and committed to the main chain with just a header. So the amount of data stored on the Ethereum chain is reduced. All the signatures are replaced by zero knowledge proof known as ZK snark, and it reduces the metadata of the signature significantly. Normally, every block header has multiple signatures, but in this case, you don't need the signature. You are replacing it with the proof that enable the compression of the aggregated transaction. The computation also is improved because you don't need to verify each signature and you just need a single snark, a succinct, non-interactive argument of knowledge. The only little bit of information that are addressed to the main chain are two Merkle root of the address book and the balance or the nonce, both of which are 32-byte field, amounting to a small part of the transaction data, which is published through call data in the smart contract. So how is it compared to other techniques like optimistic rollup and plasma? Optimistic rollups and plasma rely on challenge to an incorrect state or a root hash. In the case of plasma, it's a verification or comparison with a root hash. In optimistic rollup, you're verifying whether it's an invalid state or incorrect state, where a challenge transaction tells the smart contract that some data is incorrect and the blocks are invalidated. So it is having lot of unwanted transactions. In the case of ZK rollup, these challenges are replaced with ZK snark, where it is impossible for the relayer to submit an invalid or incorrect state. Maximum they can do is withhold it. They can't submit an invalid or incorrect state. Snark proves that the series of transactions were correctly signed by the owners and the updates to the account balance are correct, leading to leading from old Merkle root to new Merkle root. So this is how a sample ZK rollup contract look like. You have from to addresses, value, and the fee. You also mentioned the previous state and new state, and you also attach the snark proof, a short, uh, 100 to 300 byte cryptographic proofs that prove that the previous state has a state root, and it's just a proof of the previous state. And you can also apply the delta given from the list in the left. So the state delta is what you see from left to right. State delta as it is insufficient. That's why we have the detail about previous state and new state. So what you see here is hundreds of internal transactions that affect the state are compressed into a packet and into a package. So there could be 10 bytes per internal transaction that specify the state transition plus a snark proof. So these are the information in a ZK rollup. Let me now show you some of the practical. Is there any question here? If there are any questions, otherwise I'll quickly show you the applications of ZK rollup. ZK sync. So one of the most famous, I would say the most popular implementation of ZK rollup is ZK sync. You can use ZK sync for depositing from layer 1 to layer 2. You just need to open a wallet, and when you open the wallet, it will help you to link. You can connect your layer 1 wallet to a ZK sync wallet. Either you can link MetaMask or Wallet Connect, Portis, etc. So now I am trying to connect to ZK sync from my MetaMask. So right now it's showing that I am. This is my ZK sync wallet. If I have deployed any contract, I can see. If I have done any transaction, I can see. I can add contracts. For example, let's say UnChained. So I just need to give some address. Yeah, I think I have to give the standard format only. So let me first try some sample deposit. So, you can select any of the token. So you essentially need to, right now I think I'm connected to, let me check my wallet. This is in the, let me connect to my Binance. Okay, I think it is only in the Ringlebait testnet now. So I am in the Ringlebait testnet. My wallet. So I'm just getting some trial token. Let me see whether I am in which testnet. Rinky, yeah. Or let me go to Ethereum mainnet. Okay, I think I will, if you can give me a moment, I will quickly try to show you. Um, yeah, I think because I am in this session, pop-up is blocked. Yeah, so let me come back. So this is ZK Sync. You can connect ZK Sync with your MetaMask, and you can deposit your money from layer 1 to layer 2. So you can do a lot of transactions in layer 2 using ZK Sync. That is the benefit, but let me at least try to show you in the testnet. Okay. I'm just trying to log in. Please give me a moment. So I think I'm not able to log into my wallet. That's why let me try to. Yeah, I think I'm able to scan. Let's try mainnet once. Yeah, so I'll quickly show you. I hope my screen is visible. 1 second. I hope I can take 1 more minute. I'll just quickly take you through the ZK Sync. This is the mainnet of ZK Sync. So you can see block number, block size, how the block details are there, how the transactions are recorded. When you look at each transaction, everything has the fee. It's a batch transaction, and the contract, you can see the contract. Okay, and yeah, let me. So this is the ZK Sync. ZK Sync has its own contract, and you can also do quick payments through ZK Link. You can receive at payment directly on ZK Sync, and ZK Sync. One second. Another technology I wanted to show you is Hermes. Hermes is the other example of a ZK rollup based technology. Hermes has created their own token called, it's from Matter Labs. They have their wallets, and essentially they use a very simple token based payment system. So essentially it's a payment system called uh, Hermes. Hermes was developed by Ident3. And the third one is the StarkX approach. That is a ZK Stark approach. This is not the ZK Snark approach. It's a exchange, decentralized exchange, and it has been deployed by Diversify DYDX. This is an exchange built on StarkX. So if you go to Diversify the exchange, you can see this is built using ZK Rollup. So this uses the layer 2 technology called ZK Rollup. So this is a really fast decentralized exchange which is powered by StarkX, ZK Stark. This also we can connect your wallet. So this, I will, let me quickly show you an example of the code base. If anyone is interested to work on ZK rollups, the good place to start is with the ZK Sync repository. So, and anyone, if you are interested in working with me on any ZK rollup projects, you can connect with me in GitHub. This is my GitHub repo. I'll share it in the community. I think I'm able to message here. I'm not sure how to message here, but you can check it from my screen share. So here, I have also done some projects on it. It's called ZK Sync. This is from Matter Labs. This is the most accessible ZK rollup technology. So you can come to the Matter Lab repository, come to ZK Sync. If you want to set up ZK Sync, the information for setting up is available. It has a server, a ZK Sync server is there, and it has a prover and a client, JavaScript client, REST Explorer is there. Okay, and then if you look at the infrastructure setup, you can set up locally. You just need you need Docker, and you also need the Node and Yarn. There is something called Axel, that's for Mac OS. Otherwise, Rust is required, and then you need PostgreSQL, Diesel. These are the SQLX. These are the components of it, and Solidity compiler. With this much things, you can set up the ZK Sync. And when you come to the ZK Sync architecture, The ZK Sync architecture is very beautifully explained in this diagram. So ZK Sync has smart contracts, a prover application, a server application, and the server. So the if you look at the components, right, the smart contract is a Solidity smart contract, and the server is what server monitor the smart contracts on the layer one. The prover application is a off-chain application. It creates the proof for a block. It queries the server. Prover query the server. CK Sync server. Prover is connected to the server. It looks at the jobs, and if there is a new block, server. So prover query the server, and if there is a new block, server provide a witness, and the prover starts working. Once the proof is generated, it is reported to the server. Server publishes the proof to the contract. So prover talks to the server, and server talks to the blockchain smart contract. Prover is like an on-demand system, so we can have multiple prover if you need a large-scale system. And sometimes you don't need a prover at all if you're just new transaction. Generating proof requires a good machine with good CPU and RAM. Server is a node running CK Sync network. It generates the CK Sync blocks and it generates requests to the proof. Server is, it could be either monolithic server or microservice based. So this is the repository code. The contracts are here. The core, server, prover, you can find in the core. The library is here. The Docker scripts are here. The config files are in etc. So if you come to the repository, you can find it here. The contracts, ZK Sync smart contracts, you can find it here. The contracts are specifically, the ZK Sync main contract is here. Okay, and this is the main contract. You can read it. It's a very straightforward contract where you mention how to do on-chain operation, what all information you need to commit in the block, what are the input to the proof, what is the period to upgrade, and all these details. It's a workflow contract. How do you initialize it? How do you upgrade it? All this, it's an upgradable contract. That's the key. But the core cryptography is written in a smart contract known as Plonk core. Plonk is the zero knowledge proof library used here. That's the key. This is the main contract. This is based on ZK Snark called it's based on elliptical curve called BN254. So here you can find the details of the smart contract. The zero knowledge proof is here. This is the main contract. How do you do zero knowledge proof? And if you want to get started with the zero knowledge proof, what I would suggest is you can go to Remix, and you can. Some of you who are into Solidity must have used Remix already. What you just need to do is you need to install a library known as I think it is opening up. This library is if you can give me a minute, I will just quickly show that the basic you should be knowing. I will open it either in let me show you either in Chrome. I think my Chrome is coming up faster. Sometimes Brave has okay, let's see which one comes first. So I think Brave won. So if you go to here, you come to, this is the Solidity, the Remix library for writing Solidity, right? This is how you write smart contracts. So this is a sample smart contract, but there is an interesting component called Socrates. This component is used for writing proofs. Let me show you a sample proof written in Socrates. This is a very simple cryptographic proof written in a domain-specific language known as Socrates. This is a proof that there are two finite field, elliptical curve field. You are passing to private field A and B to another field called result, and the proof is if A square equal to B, then 1, otherwise 0. That means you pass true only if A square equal to B. This is the proof and return result. You can compile this proof, then you can compute the example. You can give A square equal to B. For example, the proof is 2 square equal to 4. You can give 2 and 4 and try to compute. You got 1, that means it's true. Let's give 2 and 5. When you compute, you will get 0 because 2 square is not equal to 5. Let's give 3 and 9. Let's compute. Now let's give 8. It's 0. So after the computing the proof, you can do the setup. You run the setup. So this is a trusted setup. That's what we heard first time, because ZK Snark has a trusted setup, whereas ZK Stark doesn't have a trusted setup. So when you run the setup is completed. What you get when you run the setup? You get the key. You get the key. You can get the verifier. So you run the proof is done. Now you need to verify. When you export the proof, it will open the proof. This is the verifier contract. This is something similar to the contract you have seen earlier, right? This is an elliptical curve known as BNG, BN256G2. This is written, this is auto-generated. It's the elliptical curve operation on a twisted Edward curve called BN128. It has elliptical curve operation like twisted. It's a twisted elliptical curve with addition and multiplication, etc. And so this is an example of, this is how you do basic zero knowledge proof. How do you use this in projects? Let me show you an example how we can use this in projects. Okay, I think there is a time constraint now. Our next speaker has joined. So hope I could continue this conversation later. I don't want to make Rojas wait for long. He's a friend, and all of you are looking forward to his session. So team, I hope this session was useful for you to understand the basics of zero knowledge proofs and how zero knowledge proofs is used in Ethereum for security and scalability. You can always connect with me in GitHub, Twitter, and LinkedIn, Facebook, and Instagram. Thank you so much, Razor Sec, Quill Edits, Blockchain India, for giving this opportunity. And personally, Tejaswa is my long-term collaborator in all this cryptography research, and we did a lot of research together on Ethereum security and scalability. We worked on randomness. So for me, absolute pleasure and privilege to be part of this session with you. Once again, thank you so much, all of you, to listen to me. Over to you, Tejaswa.
Same here, sir. It was a proud moment for all of us
Thank
to
you.
have you with us, and like getting information from you. And zero knowledge proofs is my favorite topic for all.
Great, great.
Yes, we'll be doing a lot of research on zero knowledge proofs
Yeah,
together.
yeah, absolutely. Looking forward to all of you coming on board in ZKP.
Yep. See you, sir. Bye bye.
Bye bye.
Hi, am I audible?
Yes, sir, you are audible.
The video,
Uh,
the screen is clear. I mean, the background, everything is clearly visible.
yeah, that's all clear. I just gonna restart the stream, and I'll. You can join in within 2 minutes with the same link.
Okay.
Cool, sir.